Okay, so the first domain that we will talk of is the family relationships domain, right? So how do we say things like Elizabeth is the mother of Charles and Charles is the father of William, okay? And rules such as one's grandmother is the mother of one's parent, etc. So those are rules which we need to put. So when we look at family relationships, all persons will be either male or female. Okay, so that's the basic unary operator for every person. And then we have kinship, which consists of two people basically. Things like parent, sibling, brother, sister, child, daughter, son, spouse, wife, husband, grandparent, grandchild, cousin, aunt, uncle, all these different things. And for mother and father, you can use functions because there's only one mother, right, or one father that a person has. So let us look at some example sentences which can be used here. One's mother is one's female parent. So for all mother and child, okay, mother of a child is equal to M if and only if M is female and M is the parent of C, right? So that is one sentence. One's husband is one's male spouse. So all for all W and F, that is the wife and husband as a variable, husband H W implies that H is male and spouse H of W. Male and female are disjoint categories, which means if somebody is male, they cannot be female. If somebody is female, they are not male. So for all X, male X, if and only if not female X. Parent and child are inverse relationships. So in other words, if X is parent of Y, then Y is child of X. So a parent PC is if and only if child CP. Okay. A grandparent is a parent of one's parent. So if you have a grandchild and child, grandparent GC, if and only if there exists some P who is a parent, okay. So G is the parent of P and P is the parent of C. If this is true, then only G is the grandparent of C. A sibling is another child of one's parent. So for all xy, sibling xy, so x is a sibling of y, if and only if there exists some parent, okay, who is a parent to both x and y. But at the same time, x should not be equal to y. So these are some example sentences in the family relationship domain, right? So if you have a number of facts, okay, for example, you can have facts like if you take a number of people, okay, so instead of taking people's names, let me take A, B, C, etc. Okay, so I can say male A and male B and female C. And we can have some relationships which are given, like for example parent. So we can say parent A, B, okay, which means A is a parent of B and parent B, C, okay. And so we can have this about every A, B, C or every person that you're writing in your family. You can have male and whether they are male or female, and can have parent relationships between them. You can have sibling relationships, And you can have rules, okay, which say things like grandparent for all x or all grandparent child, okay, grandparent g of c, and you can have a rule for this, right, which tells you, and you can have for all say x and y, siblings x, y means what, right? And you can have other relationships also. You can have things like aunt for all x, y, okay, aunt x, y. If x is the aunt of y, what does this imply, right? It means female x and whatever conditions that you want to put, niece, nephew, okay, cousin. For everything you can have rules like this. And you can have a knowledge base in which you can ask questions. Okay, so you want to know whether grandparent, say A and B or B and C, etc., right? And it will tell you whether it's true or not. Or if you say grandparent xc, you can find a instantiation for x, substitution. So x is equal to say d or some such thing. So that's how this family relationship would work. Then for numbers also you can use predicate logic. So you are going to use nat num. Okay, so nat num is a basic variable which you are using for natural numbers. You are using one constant symbol 0 and one function symbol s, which is the successor. So you can use this successor to represent anything. For example, nat num 0 if you say, so you are saying 0 is a natural number, right? And you are saying for all n, natural number n is equal to natural number successor of m. Okay, so if n is a natural number, then the successor of n is also a natural number. And you can constrain the successor function in this way. So you are saying that s of 0 is not a successor of n. Okay, if you take any natural number n which is the successor of that natural number cannot be 0. And if you take mn and m is not equal to n, then the successor of m cannot be the successor of n. So those are, and here you look at the addition, and here you say nat num, you are saying if m is a natural number, adding 0 to the natural number does not change that number, right? And here it shows you how you can add natural numbers, right? So successor of m and n is equal to successor of m plus n. So these are things which are possible for addition. Addition is the repeated application of the successor function, right? And you can also define other things continuing from there. You can define multiplication, exponential. Okay, multiplication can be defined as repeated additions. And exponential is repeated multiplications. Integer division, prime numbers, remainders, everything can be defined just using these concepts here. So next we come to the concept of sets. Okay, so if you look at sets, we know that a set is a set of objects or a list in some way where you know there's some individual objects are combined together to form a set. Okay, so we want to represent individual sets, okay, and including the empty set. So we know that empty set means a set with no elements in it, right? And we need also a way to build up a set. How do we add elements to a set or remove elements from the set? Okay. So either you can add one element to the set, or you should be able to take the union of two sets to form a set. And also member of a set, okay, is X a member of this particular set, right? So let us use the vocabulary of set theory itself. So the empty set is represented in this way, and we use the unary predicate set, which is true of sets, and we say X belongs to S, which in other words X is a member of a set S. So these are binary predicates, and S1 is a subset of S2. So two sets S1 and S2, you can say S1 is a subset of S2, and you have things like intersection, union. So S1 intersection S2 means the intersection of two sets, and S1 union S2 is the union of two sets, and X S is the set which results from adjoining element X to set S. So you are forming a new set, just adding one more element to the set S. So these are all the concepts which we want to use. So let us see how we represent these things in set theory. Okay, so we have just taken a few sentences and we are representing it using set theory. The only sets are the empty set, okay, and those made by adjoining something to a set. So for all S, set S implies that S is empty, or there exists some X and another set S2, and by adjoining this S2 to X to S2, you are getting a set which you are talking about, set S, right? The empty set has no elements adjoined into it, okay, which means if you even if you put X to S, and you get the empty set, there is no way to decompose the empty set into a smaller set and an element, basically. Adjoining an element already in the set has no effect. So you are adjoining X to S, but it's the same as the S which you had earlier. Okay, if X is already there in S, then S is the same as X adjoined to S. The only members of a set are the elements that are adjoined into it, right? We express this recursively saying that X is a member of S if and only if S is equal to some set S2 adjoined with some element Y, okay, where either Y is the same as X or X is a member of S2. So we can see how you represent this. A set is a subset of another set if and only if all of the first set's members are members of the second set. So we can say S1 is a subset of S2 if and only if there exists X such that X belongs to S1 implies X belongs to S2. So all the members which are in S1 will also belong to S2. Two sets are equal if and only if each is a subset of the other. So S1 is equal to S2 if S1 is a subset of S2 and S2 is a subset of S1. An object is in the intersection of two sets if and only if it is a member of both sets. So X belongs to S1 intersection S2 if and only if X belongs to S1 and X belongs to S2. And in the union, X belongs to S1 union S2 if X belongs to S1 or X belongs to S2. If it's either in S1 or S2, then it's in the union of the two sets. So this is the way you can represent concepts in sets using predicate logic, basically. So let us look at the Tower of Hanoi problem. So here we have actually three discs over here and three pegs. Okay, so you can remove the pegs and put them in the other, the disc can be moved to other pegs. Only thing is you cannot put a larger disk on a smaller disk. And this is your original state that you have, and this is your final state. Okay, so how do you do this of moving from here to here? So basically we need to represent some of these, the conditions, in the form of predicate logic. So we are just seeing that, of course we saw this when we did the problem solving agents, where you can look at this as your original start state, and this is your final state, and you can move from start state to the final state. So here are some of the things represented in predicate logic. So suppose we have three disks x, y and z, okay, or and a smaller xy and smaller yz implies smaller xz. Okay, so it's just saying that y is smaller than z, and if x is smaller than y, then x is smaller than z. And for all disk x and situation s, okay, so here we talk about like a situation calculus at a time situation s. X is free in situation S if and only if there does not exist a disk Y which is on X. So free X at a situation S only if there does not exist any Y which is on X. Moving a disk X onto Y is legal in a situation S only if both X and Y are free and Y is bigger than X. So in other words, you can only put a smaller disk onto a bigger disk. So this is the rule for that basically. So we can see that we can have rules in this way, right? Okay, so let us look at situation calculus here. In situation calculus, the last term which we use is the situation. So we can say situation S1, situation S2, etc. In other words, by doing something in situation S1, you can move to situation S2, etc. So, if in situation S, okay, in a particular situation S, Y is moved on to X, okay, we get situation S hat. So, S hat is equal to move X onto Y in situation S, then you get situation S dash. And you are saying that if you have other Z1 and Z2, okay, which does not have anything to moving X onto Y, okay. So it remains as it is. If Z is on X, Z is free, okay. So you are saying for all Z, Z1, not Z equal to X and not Z1 equal to Y. Then on Z, Z1. So it remains to continue on Z, Z1 even in situation S dash is what you are saying. And when you say that you are moving X onto Z, okay, free Z S hat. So at S hat you find that Z is free basically. Okay, so these are, so if it was free earlier, it continues to be free basically. So S hat will be the new situation if the move is legal. So if you have a legal move including X and Y, okay, then the situation move X, Y, S results in the situation S hat. So in this way you can use situation calculus to show how things keep moving from one situation to another situation. That is, you do a particular action, it moves from one situation to another situation basically. And then we have the uniqueness operator. So when you say exists and you use this exclamation mark there, it means that when you say there exists, you are talking about only one person who exists to do that. For example, if you have a country, the country has only one ruler. Okay, so for all C where C is a country, there exists R, who is a ruler of CR, we should have put. So, which means there exists just one person. Okay, so that is the uniqueness operator which is being used here basically. So, here are some example sentences. So, basically this part only shows you how you can represent things in predicate logic. So, we can see that predicate logic can be used to represent almost anything you want, right. So, it is a very versatile logic which can be used to represent a lot of things. So, what I am going to do now is basically go through a number of different sentences and see how to represent it using predicate logic. So, FeS is a sulfide and it is a dark grey compound. Sulfide FeS and compound FeS and dark grey FeS. No dark grey thing is a sulfide. There does not exist X, dark grey X and sulfide X. Given a robot at point A and boxes at BCD, you want to represent that the present point there is a robot at point A and there are boxes at BCD. So, you say at robot A and at box 1 B and at box 2 C and at box 3 D, and then you say that you are gathering all the boxes together, the robot gathers them all together and puts them at one particular point. So, let us call that X. Okay. So, there exists some X where at box 1 X, at box 2 X and at box 3 X. So, all the three boxes are in that same particular point. So, let us see some general sentence. People only try to assassinate rulers they are not loyal to. So, for all xy, person X and ruler Y and try to assassinate XY implies not loyal to XY. Okay, so this is an easy way of representing things. So, what I am going to do now is just go through a number of sentences which have been done in predicate logic. Okay, some students took French in spring 2022. Right. So, how would we represent this? So, we will have to say that there exists at least one student X, say, who took French in spring of 2022. So, we will have to say something like there exists some student X and you will have to say person or student X and took X French in spring 2022. So, this would be your final. There exists X student X and takes or took X French in 2022. More than one student took Greek in spring 2022. How would we represent this? We would represent like say at least two students, right? So, X and Y. So, we will have to say there exists some X and Y and you can say X not equal to Y, okay, and took X Greek in 2022 and took Y Greek in 2022, right. So, this would be represented in this way. For all X, for there exists X and there exists Y. So, I put it all together. Okay, it is possible that you can put it separately also. So, there exists X student X and takes X Greek in 2022 and there exists Y You can also put these both together out there, right? And say student X, student Y, and takes. Every person who buys a policy is smart. So we can say for all X, all people who buy, for all X who buy X policy implies smart X. We can also say person X if we want over here. Okay, person X and person X and policy P, okay, buys XP implies smart X. Okay. If it doesn't rain on Monday, Rohit will go to the mountains. So not rain Monday implies go to mountains Rohit. To the mountains, whatever, but go Rohit mountains. So you're taking mountains also as a predicate here. All basketball players are tall. So this seems to be pretty easy. So for all X basketball player, X implies tall X. For all X basketball player, X implies tall X. Some people like cabbages. So which means there exists some X, person X, and likes X cabbages. So we say there exists X, person X and likes X cabbages. Nobody likes taxes. There does not exist anyone who likes taxes. There does not exist X, person X and likes X taxes. There does not exist X likes X taxes, basically. Someone owes Susan money. So there exists some person X who owes Susan money. So this is a person X, okay, and owes, and what did we say? Person X, and we can also say person Susan if you want, and owes X Susan money. There exists as owes Susan X money. None of my friends are perfect. So there does not exist any X friend X and perfect X. Every student except Rahul smiles. So how would we represent this? We'll have to say for all X and who are students except for Rahul implies smiles X. So it would be something like this. So we say for all x, student x and x not equal to Rahul. They are x stands for all students except Rahul, implies smiles x. Everyone loves someone. So for all x, there exists some y such that likes xy. No one who runs walks. Okay. So there does not exist x such that runs x and walks x. Anyone who loves everyone loves himself. Anyone who loves everyone. So, say for all x, x is y. Oh, anyone who loves everyone. So let's say all xy loves xy implies loves xx. So you love everyone, you love yourself. So basically, I just wanted to show you how you can represent almost anything using predicate logic. So if you go to a lot of sites on the internet, you will find a lot of sentences like this where they show you how you can represent it using predicate logic. And this skill is very necessary when you're using the predicate logic to carry out reasoning in some way. So we'll stop the session here.